Okay, so yeah, good morning, everyone. So many thanks for coming to our mixed seminar of the April month. And it's really my pleasure to introduce Henrik Melin, who I have to say has been my office mate for so long, and he's a really good speaker, but he's also a really nice person and a nice scientist. And it's really my pleasure to introduce you today to him. So he is going to talk today about the giant planets, and if I understand well, you will talk about H3+, right?
Yep.
And just before that, I want just to give you a few notes about Henrik. So he did his PhD at UCL in London in the atmospheric lab. And then he moved to the US. He was working in Pasadena for a few years, and then he was back here to the UK. And since that has been working in Leicester, at the University of Leicester as a postdoc, and now this is really great. So I think just actually a few days ago he started as an STFC fellow, and in particular he's going to work with the James Webb Telescope. So it's a very specific fellowship for working with the James Webb Telescope, and we are all so happy for him because this is a really well-deserved award for you. And so, yeah, so that's my little introduction. So please, if you can share your screen, we can start with the seminar.
Can you see my screen?
Yes, we can see your screen. So yeah, when you want, Henrik.
Brilliant. Well, thank you very much for that introduction. I appreciate it. So it's really good to be here today. And I want to talk about the giant planets and particularly their upper atmospheres. And what I'm interested in is how this regional atmosphere is heated. And hopefully by the end of this, maybe at least a small fraction of you will find it interesting as well. So here's what's going to happen. Oh, nothing there. So I'm going to give you a brief sort of gentle introduction to the world of H2+, giant planet ionospheres, and what we can learn from observing this molecular ion. I'll also be talking about the energy crisis. You have to talk about the energy crisis when we talk about the upper atmospheres of the giant planets. Then I'll go through each of the planets. So Jupiter and Saturn, I'll go through some observations from pole to the equator and what it tells us about the upper atmosphere and the ionosphere. Uranus is a strange beast, and I'll try and get to some long-term trends and sort of tantalizing first glimpses of its infrared aurora. Neptune, we know so little about Neptune's upper atmosphere that it warrants 10 question marks, and I'll touch on why that is, and lastly, what we hope to do, particularly for the ice giants with the James Webb Space Telescope, and I'll wrap up. So on the right here, you have Earth and the 4 giant planets to scale. The solid line is the rotational axis, the dashed line is the dipole axis, and you can see that Uranus and Neptune sort of stands out with these sort of highly offset magnetic fields, making them, in my mind, very, very interesting. So let me start by defining what the upper atmosphere is. So the upper atmosphere is anything above the homopause. And the homopause is the line at which eddy diffusion, that's the turbulent mixing we see in the lower atmosphere, where the eddy diffusion equals molecular diffusion. So essentially, above the homopause, all the species fall out according to the molecular weight, their scale height. And that means all the heavy stuff like hydrocarbons and helium sits basically at the base of the homopause, and the rest of the upper atmosphere is dominated by molecular and atomic hydrogen. That means that this region is of very low density. It has 2 principal components, and that's the neutral thermosphere, and within the neutral thermosphere sits the charged particle ionosphere. Because the upper atmosphere is dominated by atomic and molecular hydrogen, the dominant ion in the ionosphere is He+, and of course protons, but you can't observe those readily. He+ is observed from in near infrared using telescopes, either on the ground or in space, like the James Webb Space Telescope. So why do we even care about this region? Well, the ionosphere is of course charged, and it feels a magnetic field, and therefore it becomes sort of this interface layer where energy is transferred between the atmosphere and the magnetic field, and vice versa. That's illustrated on the left here. So at Earth, the raw currents driving joule heating, for example, in the upper atmosphere. On the left, so on the right, we have a schematic showing some of the processes that occurs within Earth's ionosphere. We expect all of these, well, most of these, if not all, to be present at the giant planets as well, but with more ferocity. You know, these planets have very strong magnetic fields, they're massive, and they spin really fast. So there's going to be some really interesting features, particularly at lower latitudes, and something we're beginning to learn at the giant planets right now. So H2 plus was discovered in 1911 by J.J. Thomson. He also made a some less significant discovery of the electron, but you know, obviously H2 plus is clearly more important. When you have any volume of molecular hydrogen and you inject a source of energy source into it, either solar photons, EV photons, or auroral particle precipitation about the magnetic poles, you create H2 plus. You pop an electron off molecular hydrogen, and you get H2 plus. The H2 plus is very quickly converted to H2 plus via this reaction. It's exothermic, so there's really no H2 plus in the atmosphere at all. It's all converted to H2 plus. And the intensity of H2 plus is given by this equation here. Don't worry too much about what's in it, apart from two terms. It's linearly dependent on the number density of H2 plus ions and exponentially dependent on the temperature. And I'll show you what a spectrum looks like in the next slide. So this is sort of a synthetic spectrum, and I'm going through a range of temperatures from 300 to about 1200 Kelvin. And you can notice, so this is a spectral resolution of 800, so intensity versus wavelengths. You can see two things. As you increase the temperature, the intensity goes up. As you go up above 1000, the rate of increase sort of reduces slightly. The second thing you can see is that the relative ratio of these lines changes dramatically with the temperature. And we use these effectively line ratios. That's like a simple way of doing it. So you have those two lines highlighted in purple. If you take the ratio of those, that's sort of a very good proxy for the temperature. We can do something more sophisticated by using all the lines fitting the spectrum, of course, as well. So this gives us a means by which we can measure the temperature of the upper atmosphere of the giant planets. If we plot those two lines out like this is intensity per molecule, sort of theoretically calculated. And those two lines, we call them Q1 and Q3, some of the brightest lines that we have in the near infrared H2 plus spectrum. So we can see that the intensity goes up exponentially as a function of temperature, and the line ratio changes with temperature as well. So the two lines are equal about 750 Kelvin. So if you see a spectrum as you're getting the data down from the telescope, you can very quickly determine whether something's hotter or cooler than 750 Kelvin. I put the sort of approximate temperatures of the three planets, Saturn, Uranus, and Jupiter, on here. Clearly, Jupiter is quite hot, and so the H2 plus emissions is quite intense, whereas Saturn is quite cold, which means that it's less intense, and because it's less intense, it's also harder to observe. So there's an intrinsic challenge in observing cold H2 plus emission versus really hot stuff. And if you want to have a go at modeling H2 plus yourself in a sort of 21st century manner, you can try out this spectral modeling package we put together at Leicester. So H2 plus PY, maybe happy, I don't know. So it's Python 3, you can model spectra. Here's an example. This is the first ever spectrum of H2 plus obtained from Uranus. And I've fitted it with this package as well. So it does work. And if we're going to play around with it, please do so. And if you have any feedback, please let us know as well. So what can you learn by observing or analyzing the H2 plus spectrum? Well, of course, you have what you get down from the telescope is H2 plus intensity. So, and through spectral analysis, like I showed, you can figure out what the temperature is of the upper atmosphere of these planets. So assuming H3 plus is thermalized, i.e. the LTE applies in the upper atmosphere, the ionospheric temperature equals the thermospheric temperature. And we sort of think this is a pretty good assumption, particularly lower down in the denser part of the upper atmosphere. The temperature maps essentially a heating process in the atmosphere. So we have a heating where Joule heating occurs in the polar atmosphere, and I'll talk about some other heating sources a bit later. From the spectral analysis, we also get the column integrated H2 plus density. And the density is a tracer of ionization rates, essentially. Where you have high densities of H2 plus, you must have a large ionization source. And so by tracking the densities, we can look at the morphology of the injection of energy, basically the electron flux into the atmosphere, and study auroral morphology and the origin of these auroral features we see in the polar atmosphere. By combining the temperature and the column density, we can calculate the wavelength integrated intensity. And that's the energy that H plus radiates over all wavelengths. Now, H plus is an extremely efficient emitter. It's 10 to the 10 times more efficient than molecular hydrogen in the near infrared. So it's actually quite a powerful cooling mechanism, removing energy from the upper atmosphere, radiating it into space. Another cool thing you can do with H plus, if you have a high resolution spectrograph, something over 20,000 maybe, you can actually measure the Doppler shift of these H plus emission lines, basically the wavelength shift due to the motion of the ions in the atmosphere. And that gives us the ion flow speeds inside the atmosphere. So this is a line of sight velocity. And that tells us very important things about the dynamics of the ionosphere. Essentially, the magnetospheric forcing, how the magnetosphere sort of pulls, tugs and pulls at the ionosphere. And this is sort of a unique data set. I don't know any reasonable other way to go about doing that. Another cool thing you can do, you can measure the intensity, so the spectrum of H plus above the planetary limb. And this is the one way to get a vertical profiles of the ionosphere and upper atmosphere. Normally, we have these nadir observations where we're looking down on the planet and we're getting these column integrated densities and sort of column averaged temperatures. By doing these limb observations, we can actually separate things out into altitude. This is particularly useful if you have a spacecraft around the orbit of, say, Jupiter, like Juno. So that's neat. So you can't really talk about the giant planets without mentioning this energy crisis. So the Voyager spacecraft, Voyager 2, visited all of these planets throughout the 80s, late 70s and throughout the 80s. So Jupiter in 79, Neptune in 1989. And this is the first real close-up view we got of the four giant planets. So the initial thinking before Voyager 2 got there was that the upper atmospheres of these planets was likely very, very cold. These are planets that are really far from the sun. Jupiter receives less than 4% of the sunshine we get here on Earth, and Neptune gets less than 0.1% of the energy flux we get from the sun. And so the Earth, the upper atmosphere of the Earth can be explained very well by the solar input it receives. And so the thinking was that the upper atmosphere of these planets must be very, very cold, which is why it was a huge surprise when we got back the data. Well, not we, other people got back the data, and so the prediction was very, very cold. The observations showed very, very hot. And so the upper atmospheres are hundreds and hundreds of kelvins hotter than the sort of solar input model predicts. And this is a huge challenge because we fundamentally do not understand half of the atmospheres within our solar system. Where is this energy come from? And it's not just a thing that happens at the pole. This is the global, they're too hot, basically all over. So that's the energy crisis. And that's something that's been unresolved for over 30 years. So what are the potential solutions to the energy crisis? Well, there's been sort of two competing theories. Firstly, we have the auroral process, whereby vast amounts of energy is injected at the poles. So we certainly have enough energy there. The question is, how do you move this energy down from the pole down to the equator? And these planets are really fast rotators. They're massive and therefore have immense Coriolis forces. They effectively prohibit energy moving from the pole down to the equator. So it's not an easy solution at all, although there's lots of energy in the poles. Secondly, we have wave heating, here gravity or acoustic waves generated at the turbulent lower atmosphere and troposphere. Essentially, they travel up in altitude through the stratosphere into the thermosphere with a break, and they release their energy. We have one observation, which I'll come to talk about, which shows this at Jupiter, but otherwise evidence is a bit scant. So just to reframe the energy crisis slightly then, understanding the energy crisis comes understanding how energy moves within and between different atmospheric layers. And largely our observations are lacking, but I'm going to show you today some of the evidence we have in hand. So we're going to start with Jupiter. That's Jupiter. So obviously this is emission of Hg+ as observed by the Juno-Gyram spacecraft. The Juno-Gyram has two basic components. It has a spectrograph and it has an imager with two different filters. This is the L filter at 3.5 microns. This shows the southern aurora of Jupiter over a time span of about 45 minutes. And you see some really interesting features in here. The moon trails, the Io trail, the dashed white lines, a little hard to see. But you can see the trails of the moon, which provides sort of an absolute magnetospheric mapping for these observations. And that's what Jack Canoni used to develop his VIP 4 model back in the late 90s, for example. So you can see an aurora that's highly dynamic. Aurora is currents going through the magnetosphere, heating it by way of Joule heating. And this has been observed as well. So we go from pure intensities now to temperature. And this is sort of a seminal paper by Rosie Johnson, which looked at the temperature of Jupiter's auroral region in whenever it was. I haven't got it on there, but yeah, it shows you the temperature here. So it was about 6 different scans of the northern aurora of the VLT Criris, about 4 microns, which captures a number of Hg+ lines. From these Hg+ lines, you can derive the temperature, and that's shown on the top left here. And the first thing to notice, of course, is that the aurora is really hot. We're talking 900 kelvins on that dawn side. It's somewhat cooler on the dusk side, and we have this sort of mysterious, I don't know if you can see my pointer, but we have a band of heat which sort of goes across the swell region, which is really interesting because there's lots of dynamics there. This is, of course, just one example. There's not a lot of statistics in here, but it shows some really interesting features: a hot dawn region, a sort of cooler dusk region. The intensities are at the bottom, which is, of course, more symmetric, and that's the intensities is densities and temperatures entwined, essentially. So one of the interesting things that Rosie did, because CRIRES is a really high resolution instrument, you can also measure the ion winds, the line of sight ion winds, at the same time we measured these temperatures. And that's what I'm showing here. So at the bottom plot, you have the Doppler shift of the Hg+ emission lines, which gives us the line of sight velocity. We convert that to kilometers per second. And so 0 in the bottom plot here is the co-rotation with Jupiter. So system 3 rotation. Anything departing from that, either redshift or the blue shift, is going slower or faster than the rotation of the planet. So naively, just looking at the velocities, you may expect lots of heating to occur where you have a large shear between the neutrals.
I'm just wondering what time you're likely to get here, that's all.
Katrina. where was I? Oh yeah, so naively, you may think a large shear between the neutrals and the ions may give rise to high Joule heating rates, because you basically have a stream of ions going through neutrals. But looking at the comparing the temperature map to the ion flow map, that's not necessarily true. We're seeing perhaps a correspondence to large ion velocities and high temperatures on the dawn side, but it's much less clear on the dusk side. We have high departures from co-rotations in the ions, yet there isn't much heating going on. Of course, there is something we're missing here. We don't actually know what the neutrals are doing. We have this sort of naive assumption that they're rotating at the system 3 rate, but that may not be true. You know, we have heating in the thermosphere, and the heating is in itself going to drive dynamics and winds in the thermosphere. So this is something we need to figure out in the long term. What are the neutrals doing relative to the ions? Rosie also showed really interesting short-term changes in the temperature of Jupiter's polar atmosphere. So it was 6 scans. At the top, we have the first 2. So we have the temperature on the left and the difference, the change in temperature on the right. So super interesting. We have 2 regions highlighted, A and B. A starts out hot. About an hour later, it's about 100 Kelvin cooler. B starts out cold, and an hour later, it's maybe not 100, but 100-ish Kelvins hotter. And so this is really intriguing, right? How does something change in very short timescales by 100 Kelvin? Well, one potential answer could be that the energy of the precipitating electrons that ionize molecular hydrogen to produce Hu+ changes. So the energy of the electron changes means that we're sampling different altitudes, and different altitudes samples different temperatures on the temperature of the upper atmosphere. So the very top of the upper atmosphere is hot. As we descend in altitude, the upper atmosphere gets cooler. So if you have low energy electron, you're likely sampling higher up in the atmosphere compared to lower energy electrons. Or this can be some local time behavior, but we really haven't got a good handle on the short-term changes. This is really the only good example we have. Okay, so we now know that there's lots of energy in the polar region. And to solve the energy crisis, we somehow need to redistribute that energy down to lower latitudes. And this is a study by James O'Donoghue from 2020, from this year, data from 2016 and 2017, taken with Keck and Keck. So you put the slit across the central meridian and you observe the planet rotating underneath the slit. And there's a couple of really interesting things here. We look at the bottom plot, which shows temperature as a function of latitude for the 2 different dates. Firstly, you see this very gradual temperature gradient from the pole down to the equator. And this hints at the possibility that aurora can actually overcome those strong Coriolis forces to sort of move down towards lower latitudes. So that's a hint number 1. You can also see that there is variability between the 2 days. I mean, obviously the separation is almost a year, right? There is some variability, maybe 100 Kelvin in the temperature of the lower latitude ionosphere. Super interesting. Secondly, well, thirdly, at this stage, I guess, on the top right plot on the 25th of January, 2017, you have this polar view, see the aurora, and you see this band south of the main auroral oval. And it's like, as if it's we have a band of heat moving towards southern latitudes. And this is actually something that was modeled by Yaffe Yates in 2014. He used a variable solar input, as variable solar wind in his case. You can probably do it with Io volcanic activity as well. You have a highly variable aurora, which we already know Jupiter's aurora is, and you get this wave of energy. So here we have latitude versus altitude. And this is a change in temperature, but these waves that propagate down towards lower latitude. So it could be that the variable aurora allows us to penetrate, to move heat down towards lower latitude. as suggested by model. James did a cool animation for this. I just thought I'd show it to you. This Jupiter, and here's the artist impression of these waves moving down as the aurora varies, producing these waves traveling down towards lower latitudes. And then we'll have the data. It's pretty nice. Okay. A different way to heat the upper atmosphere of Jupiter is this wave heating process, where you have waves generated in the lower atmosphere. They propagate up, they break and release their energy in the upper atmosphere. This has been observed exactly one. This is James O'Donoghue again, observing pole-to-pole temperature measurements using the spectrograph on RTF. And this region here, highlighted gray at the top, shows you the temperature in red, where the great red spot is, and in blue, away from the great red spot. And we're seeing some extreme temperatures right above the great red spot, which indicates that this sort of wave heating is a powerful way to heat the upper atmosphere. We have some observations since that hints that this is still an important process, but maybe less fervent than it was back when this observation was done. So moving down latitude, just show you some cool stuff. Here we have Tom Staller's 2018 paper that shows you a latitude longitude map of H2 plus emissions at low latitude. And this is shown as a percentage of the main auroral brightness. He used a large number of RTF NSF scan images to produce this. And it's super interesting. You're seeing some really intriguing features in the low latitude ionosphere of Jupiter. And what's even more of a trip is that if you overplot the magnetic dip angle of the latest, well, at the time, the latest Juno magnetometer field model, you get that it almost perfectly aligns with features in the magnetic field, and it shows the magnetic dip angles. You see the black ribbon going across, coinciding with a dip angle of 0. Maybe that's analogous to something like the plasma fountain at the Earth. You see these dark spots, we have minimum, perhaps perfectly aligned there, but very, very interesting. So we don't actually know exactly what's going on here, but yeah, this is really our first glimpse at the detailed low latitude ionosphere at Jupiter. You can also see this in Lyman alpha, and this I used some Cassini data from the Jupiter flyby to map the Lyman alpha emission on the body of the planet. That's a function of latitude and longitude. And you see this asymmetric emission feature. And we've known about this for decades. So we saw it with IUE, John Clark saw it with IUE back in the 80s. And this actually coincides with, if you plot the location of this brightness, that coincides as well with this magnetic field, the dip angle of the magnetic field. So you have a situation where you have dark H2 plus, and you have bright Lyman alpha. So you could perhaps destroy H2 plus to produce 3 molecular hydrogen by a recombination with electrons. I don't think that would produce enough atomic hydrogen, but there is something happening there which is intriguing, and we don't really know what it is yet. So let's move on to Saturn. I'm not going to talk a lot about Saturn because Saturn is hard. Saturn is difficult. Because it is cold, H2 plus is weak, and so we need really, really big telescopes to do it. So just to show you how cool Saturn is, here's some work I did for my PhD. I used CGS-4 on UCURT, now defunct UCURT in Hawaii, and got temperatures of about 400 kelvins in the polar region. Compare that to about 1,900 at Jupiter, rendering H2 plus a lot weaker and a lot harder to observe. And so we need big telescopes to do it, and that means the data is quite sparse. But another way you can measure the temperature of the upper atmosphere of Saturn is to use stellar occultation. And this is some excellent work done by Zara Brown using the last orbits, the grand finale orbits of the Cassini missions, during which a number of stellar occultations were taken to complete the latitude coverage that we had to date. And so here we have temperature as a function of latitude on the bottom left here. And of course, we see temperatures that are much higher than solar input alone. That's the dotted line. But we also see this temperature gradient that we saw at Jupiter, that James O'Donoghue saw. And so there is a gradual slope of temperature down towards the equator, which is what you'd expect if the energy injected by the auroral process were able to be redistributed down towards lower latitudes. Now, the dashed line here shows you a model by Ingo, where he sort of employs this novel thing, which is gravity waves impart momentum, loads the upper atmosphere with momentum, which has the effect of slowing it down, which means the Coriolis force is smaller, enabling this movement of energy down towards lower latitudes. Interesting idea, and I think more work needs to be done to test that. We can do perhaps with observing neutrals again, like at Jupiter. We're also seeing some interesting long-term changes in Jupiter's atmosphere. Here we have work by Tommy Koskinen, again stellar and solar occultations by the Cassini spacecraft, and reanalyzed Voyager occultations in purple. So on the right, you have sort of a similar thing that Sarah did. We see temperatures much higher than the solar input predicts. That's cool. On the right here, we have those temperatures. So inside that blue box, you plot the temperatures down at much lower altitudes. So on the left, you have the exospheric temperature. That's right atop the atmosphere. On the right, we have temperatures much closer to the homopoles. From these observations, you basically get a temperature profile. So you plot those temperatures as a nanobar level, as a function of time, and you do see a peak, what appears to be a peak at equinox. And of course, there's only 3 points subsequent to equinox. So this could make sense. You have the highest solar flux at the equator of equinox, so maybe it's hottest at equinox. But then again, the energy crisis means that the temperatures are not necessarily driven by the solar input, but it could provide some, say, conductivity and things like that. Lastly, with Saturn, we talk very briefly about ring rain, and this is the low latitude process. And really, we have limited observations of this, but it's been confirmed by the Cassini grand finale orbits. So on the top here, we have the observational setup. We have Saturn with a slit going across the middle. We have the emission lines, so bright at the aurora going down, and there's the rings, and the aurora again at the bottom. And so you plot the intensity of H plus as a function of latitude, and what you find is there are magnetically conjugate features in the ionosphere, because Saturn has a field that is offset off the center of the planet, which means sort of the magnetic latitude and geographic latitude are not the same. So you see these features which are magnetically conjugate, and they're linked to features in Saturn's rings. And that means we have material flowing from the rings into the planet along the magnetic field lines. And this, of course, you have charged particles following the field line, you essentially have a current. Could this be a source of energy for Saturn's lower atmosphere? It's an interesting question, and yeah, we don't know yet, I suppose. So let's talk about Uranus. Of course, Uranus is a right weirdo. So it has a rotational tilt by about 90 degrees. It rotates in the plane of ecliptic. It has a magnetic field offset some 60 degrees from that. And so you have this weird situation, like the day on Uranus is 17 hours. Every 17 hours, the magnetic field flaps around and changes directions with an interplanetary magnetic field every day, which is kind of intense. And we don't really know what that means for the ionosphere. Well, the auroral process, I guess, essentially. So Voyager 2 flew by in 1986. It produced this gorgeous map. Well, it's what we have. Latitude versus longitude. And we see this patchy emission sort of mainly located on the day side part of the magnetosphere, so maybe it's cusp related. And this aurora is incredibly weak. We're talking hundreds of Rayleighs, whereas at Jupiter, you talk about hundreds of kilorayleighs, about at least 1,000 times weaker than at Jupiter. And here I just, on the bottom left here, I just remapped the observations to what they look like in equinox. Because the magnetic field is offset, the aurora actually occurs on the equator, which could actually help us. You have aurora on the equator, you don't have to worry about Coriolis forces. Kind of interesting. So you've observed the Hubble Space Telescope. HST has observed the aurora of Uranus. It is very challenging observations. You have 1 sigma essentially of the background of white, a dot there, something there. Well, it's very challenging stuff, but at least it appears spotty, a bit like the UV observations by Hubble. Just to compare that to the gorgeous Hubble images we get of Jupiter's aurora, makes us a bit jealous. We have some absolutely outstanding work done by Emma Thomas here at Leicester. She used Keck-Neespec data from 2006 and basically mapped the temperature and intensity and density of He+ across the disk of Uranus, producing, this is the intensity I'm showing, but these brightness features are not driven by temperature, they're driven by density, and density means enhanced ionization of molecular hydrogen. And that means you have to have an ionization, a localized ionization source, and that is an obvious candidate for that is aurora. So this is the first time we've seen sort of what resembles an auroral oval at Uranus. And why can't we see this in UV? Well, maybe the UV can only see the very brightest of the aurora, whereas He+ perhaps can sample some of the more finer details. TBD. So something I've been working on for quite a while is to look at the long-term temperature trends in Uranus's upper atmosphere. And I've basically gone back and reanalyzed every single data set we've had, including since the discovery in 1992. So using a number of facilities, a total of 885 nights since 1992. And we've really ramped up these observations since about the last decade or so, just to get this study, get some data for it. And so all I do is get the globally average temperature per night of observation, and then I produce a yearly average, and I plot those as a function of time. And here's what they come out as. Really quite interesting. So when Voyager 2 got Uranus, got a temperature of about 750 Kelvin in the upper atmosphere. This is consistent with this. But since then, we've observed cooling at Uranus. So about 30 years or more of cooling. And what's weird about that is nominal season at Uranus is 21 years. It takes Uranus 84 years to go around the sun. So cooling has been going on for longer than this nominal season. Super interesting. And there's another consequence of this. So, Uranus goes from hot, so almost Jupiter hot, to Saturn cold. And that means that it's becoming harder and harder to observe. And so as our telescopes and our instruments have become more powerful, Uranus is sort of fighting back in a weird way to become harder and harder to observe. What's causing this? Well, it's likely linked to its weird geometry. And here's some high-class clip art to illustrate that. So you can have a scenario which I call geometric season, where you have some kind of offset in the variability due to thermal insulation, perhaps, and you have this pattern that varies. You get peak at solstice, offset by a little bit, a trough at solstice, offset by a little bit, or you can have what I call magnetic season. So here, because the magnetic field is offset from the center of the planet, one solstice does not equal the other solstice. So the geometry with respect to the solar wind is actually a little bit different. I don't know if it's different enough, but you could have a scenario where you have lots of heating in one solstice, and sort of the umbrella at the top here shows that as the other solstice is more protected, protected from the solar wind. There's not going to be much reconnection producing aurora and then dual heating, perhaps. Right, that's what I have for Uranus. Let's talk about Neptune. And Neptune is basically those 10 question marks, right? We have maybe an observation of the aurora from Voyager 2 in 1989. So someone's attempted to map it here. We have a brightness of 10 Rays at the maximum. Remember, the aurora at Neptune was 100, at Jupiter's were 100 kilorays. So this is really not very much at all. And so the open, what do you call them? Open, non-filled points here, the circles, is one rotation of the planet followed by a partial rotation in black. And so maybe there is an aurora here, and that corresponds to this peak here, but the signal to noise is just, it's intense. So we can't really say much about that. What about H2+? Have we seen H2+ from the planet? Well, what could we expect? So here's two models of the Uranus's upper atmosphere, predicting about 100 ions per square centimeter, cubic centimeter. And if that was actually the case, it would be detectable. So obviously people have tried, I've tried, and here's a couple of examples of us trying. So Keck observations is a paper published in 2011. So you have sort of a spectral image, Neptune at the top, Uranus at the bottom. You have really gorgeous H+ emission lines of Uranus. You co-add them, you get something great. Neptune, you get absolutely nothing. There is absolutely nothing there. You co-add it, yeah, nothing. And I did the same with ice shell. I spent 15 hours staring on the planet, saw absolutely nothing. So where is the H+ at Neptune? Where has it gone? Well, either the models underestimate the density for some reason, or maybe the upper atmosphere of Neptune has also cooled, similar to Uranus. Luke Moore has an interesting paper at this, published in 2020, if you want to know more. But Neptune remains a massive mystery, and we have to get somewhere in understanding, the ice giants as a family. So let me just summarize a little bit. So here's a comparison between looking at the energy crisis between these different planets. So Jupiter, you have lots of energy. You have the brightest aurora in the solar system. You have evidence that the heat can be redistributed from the pole down to the equator. And you also have evidence that these gravity waves generated in the troposphere can break in the upper atmosphere. You also have, the same as Saturn, we have a much cooler ionosphere, which means that the energy crisis is not as severe. But the aurora, the same as Jupiter, you can probably redistribute the energy from the pole down to the equator. There are also long-term changes in the temperature of the upper atmosphere, but not in the same way we see at Uranus. We saw a downturn trend at equinox at Saturn. We don't see that at all at Uranus. It just continues to cool. Uranus is basically very limited aurora. How can you maintain high temperatures with basically no aurora, and really no storms in the troposphere? There's no internal heat at Uranus. So how do you generate these waves without a stormy atmosphere? Neptune was certainly hot in 1989. And we've not really learned anything new about the upper atmosphere since, apart from maybe the models are wrong or it's cooled. So what we really need, of course, is the James Webb Space Telescope. Basically the most advanced telescope ever built. It has a 6.5 meter mirrors and is now in orbit at L2. It has 4 different instruments. I'll be using 2 of them, and that's MIRI, built partly at the University of Leicester, and MIRI, the mid-infrared. MIRI and NIRSPEC. I should know this. It is, of course, not servable out at altitude, unlike Hubble. Although I did learn it has got an exposed fuel tank, so you can actually build a spacecraft to refuel it somehow. I thought I'd show you this just because it's awesome. This is on the Christmas Day last year. We got to see it live just before Christmas dinner. And that neat. James Space Telescope actually in space, and it has since completed its unfolding or origami-like unfolding. It's got its 60 centimeter high gain antenna out, which allows transfer speeds of 3.5 megabytes a second. It's unfurled this absolutely massive sun shield, the size of a tennis court, 21 by 14 meters. The sun shield is this aluminium covered kapton, basically these space blankets you get, and it provides outstanding thermal insulations from the sun's radiation. People compare it to a beach umbrella or whatever. The hot side is 85 degrees Celsius, so almost a boiling point, whereas the cold side is 40 Kelvin. So I've heard someone compare it to an SPF of 1 million or something. So pretty extreme thermal design. We've now got a complete telescope, and everything's worked perfectly from launch to this deployment process. And last week or so, we got the first sort of proper image. I would say it's a picture of a fairly boring star, the K magnitude of 4.7. But what's interesting about this image, of course, is not the star. It's all these hundreds of galaxies just appearing in the background. So in a simple 15-minute exposure, you sort of automatically get a sort of a deep field observation of the distant universe. It's pretty extraordinary. So what are we going to do with James Webb and the giant planets? Well, we have some programs in the GTO and the ERS programs. We look at Jupiter's, the ionosphere right above the Great Red Spot to see where the heating occurs relative to where the storm is. Look at the southern auroral region as well. But where the real beauty of these instruments come is the ice giants, right? Because the field of view of, so NIRSPEC has this integral field unit, which is 3 by 3 arc seconds. And on Jupiter, that's basically nothing. You see a little postage stamp of something somewhere. So you have to do mosaicing and things get really complicated. But at Uranus, we basically cover the whole disk of Uranus, and we're going to get the first complete mapping of Uranus's ionosphere. And we'll do the same with Neptune, and maybe we'll be able to detect A2+ for the very first time, which would mean the first characterizations of Neptune's upper atmosphere since 1989. That's a long time. The real power is combining different instruments, though. We can use NIRSPEC and MIRI to get spectral coverage from 2 all the way out to 28 microns. And that means we capture emissions from the entire column of atmosphere, from the troposphere through the stratosphere, all the way up to the upper atmosphere. It's the first real cohesive view of the atmosphere as one interconnected system. So yeah, it's going to be super exciting. And hopefully get the data this summer as well. So exciting, and it's going to be busy. So this is my last slide. We sort of learned here that at Jupiter and Saturn, there is some evidence that energy is distributed from the poles down to the equator. How does this work for Uranus and Neptune? We don't really know. There's some evidence at Jupiter that the Great Red Spot has some Weber acoustic heating. How important is this process globally? Jupiter is basically a planet full of storms. Could this happening on a micro level everywhere? With Neptune and Uranus having limited auroral activity, how can you generate strong enough Joule heating to heat the upper atmospheres? Why are those planets so hot, with seemingly limited inputs? And of course, we're banking on James Webb being awesome. Well, that's it. Thank you.
Thank you so much, Henrik. And yeah, I think it has been a really excellent seminar. I think everyone is really excited with the James Webb Space Telescope. So I'm really looking forward for when you get the data this summer. So is there any question for Henrik in the audience? I think you can just open your microphone or raise your hand or use the chat as you prefer. I want to open also here the list of participants so I can see that. Okay, so maybe while people, maybe they are writing or whatever. So I have a question. When your models for Uranus, when you were talking about the gradual cooling that you are observing in the aurorae emission. So I was wondering actually if it's a mix of both of them, because it seems that, I mean, geometrically, there must be an effect, right? But of course, magnetically, this is also important because in the end, it's the solar wind interacting. So do you think it could be like a combination of both of them?
Yeah, it could be. I think the trick here is going to be to continue this trend into the next decade or 2 decades. What's going to happen to the temperature? Because both of these, I mean, these aren't really models. This is sort of hand wavy stuff. But you have minima coming up very soon or within a decade, and so keeping an eye on these temperatures, I think it's going to be.
There is also like small variations, right? Like there are some data that are a bit hotter than the surrounding ones. Those ones, yeah. We have a theory about that because that's in 2014, I think, and in 2016. Anyway, at some point, but that coincided with an outbreak of a massive storm at Uranus. So we're sort of thinking maybe that had an effect of producing a temporary heating of the upper atmosphere, which then sort of subsided. But yeah, it's true. There is significant variability within this data set, and that variability is sort of traditionally been interpreted as auroral. So you have a background atmosphere on top of which we have auroral variability. But Emma's work is really going to help on that as well. Yeah, this is really interesting. So let's see the coming observations. If you continue with the minimum or not.
Yes.
Okay. I think Steve has a question. Maybe Steve, you can open your microphone.
Hi there, Henrik. Great seminar. Thanks very much. I was wondering if similar processes are seen at Earth. Do you get transport of heat from auroral latitudes towards the equator at Earth? Obviously, much less significant, but is that something that's been observed?
It's a good question. Because at Earth, the thermal structure of the upper atmosphere is largely governed by the sun, although there is heating at the poles. Yeah, that's a good question. I should look at that.
Good. Any other questions for Henrik?
I had a question about how you can, like, I don't understand how James Webb Space Telescope works. So we're normally used to using like long slit shell spectrometers, but it's going to be like, like it's looking at all of Uranus at once. So so how does that work then?
Yeah, so it's actually pretty cool. So you have what's called an integral field unit. So there's a field of view with 3 by 3 arc seconds. But within that, you call them spaxel. It's like a spatial, I don't know what it's called. But so you have 30 pixels in the y direction, so 30 pixels in the x direction. And each of those pixels will project onto a detector. So you have 30 strips, each 10 pixels high. So you basically get a data cube. So two spatial dimensions and 1 spectral dimension. So you get a 2D spectral cube in one shot, which is pretty awesome. But this 3 by 3 arc second is of course tiny. It's really good for Uranus and Neptune. For Jupiter and Saturn, you have to do masaking and things change over time. So yeah, it's both Miri and NeoSpecs have these integral field units, so they're going to work really great together as well. Does that make sense?
Yeah, thanks. And thanks for your seminar. It was really like a nice summary of all the H3 plus stuff.
Indeed, it is. I don't think there is any other question, but please, if you have any question, just open your microphone. And I don't see anything on the chat either. So yeah, if there are no more questions, so I think we can finish the seminar here. So thank you so much, Henrik, for your time and for the excellent seminar. So the seminar will be uploaded after, like in the next hour, to YouTube, and I will send an email to everyone. So yeah, because I'm sure there are more people that would like to see the seminar but couldn't connect now. And just a reminder, like the next seminar will be the first Tuesday of May, and it's in this time. Next time will be Chris Owen talking about solar orbiter. So yeah, thank you so much to everyone, and really have a nice day, and hopefully a good Easter time, everyone. Cool. Bye.
Thanks, Petrus. Bye.